We are Team Vortex, Team 14969, and in this video we're going to be showing you how to go about path planning for FTC. So, we will go over using the FTC SDK for motion control, and we will go over how to set up the motors in the control hub and how to initialize them and use them in the code. Next, we'll implement acceleration and deceleration so your robot can slowly accelerate and decelerate. Next, we will show you how to use encoders for accurate movement and motion control, and then we will give you links for how to set up Roadrunner, which is a library used for motion control and motion planning, and we will write some simple code with Roadrunner. Let's go over using the FTC SDK for motion control. So, to start, what you want to do is you want to plug in your motors into the control hub. So the control hub looks like this, and there are many ports on the control hub. So these ports right here are for servos, these ports right here can be used for sensors, and these ports right here are for motors, and this port right here is for the battery. So what you want to do is you want to plug in your motors into these ports. So there are two ports. There is one for power, this big one right here with 2 prongs, and one for an encoder, which is here with 4 prongs. We'll go over encoders a little bit later. So you will plug in your power cable right here and your encoder cable right here. And note the number that is right here. This will be important. So this is port 0, this is port 1, this is port 2, and this is port 3. You want to note these numbers because they will be used when you are configuring your robot inside the driver station app. It is the same process for servos. What you want to do is you want to plug in your servos into these ports right here, and you want to note these numbers right here as they will be used in configuration for configuring your servo. Next, what you will need to do is you will need to configure your motors and servos inside of the driver station app. We will provide a link in the description with a video on how you can do this. So, once you have wired and configured your motors and servos, you will need to set them up inside your code. So, you can create 4 variables for your drivetrain. You can have a public DC motor, FL motor, and you want to set this to null right now. And you want to do this for all of your motors. So FL motor or front left motor, FR motor or front right, BL motor back left, and BR motor back right. And you can do the same thing for your servos. You have a public servo claw, let's say, or a public continuous rotation servo. This is what CR servo stands for. Intake, and then you have a servo capping, and then you have another servo for a box cover, let's say. Now, next what you will need to do is you will need to initialize your hardware map. So you want to create a hardware map, and then name hardware map, and you want to set that to null right now. So next you will need to initialize these motors. So you need to set them to FL motor or whatever variable name you use up here, and you need to set that to hardware map, or we set it to up here, we set it to hardware map HW map dot get DC motor dot class, comma, and whatever name you use in the configuration. So if you use left motor or right motor, you would need to put that in the exact same form you put it in there. Capitalization counts. So in our configuration, we have FL motor, BL motor, FR motor, and BR motor. And you can do the same thing for the servos, except you want to do servo.class instead of DC motor. Next, you will need to set it to if you were using an encoder or not. If you are using an encoder, you want to set it to run using encoder. If you aren't using an encoder, you want to set it to run without encoder. And it's just FL motor.set mode, and then DC motor.run mode.run using encoder. Next, you will need to set the direction. You might need to test your motors out for this. For you to get it right. You probably won't get it right the first time, but you can set some to forward and some to reverse. So for us, we have the left motor set forward and the right motor set reverse. For the servos, you just want to switch it to, instead of DC motor, you want to put servo.direction. And here, these functions are just to stop and to reset the encoder values. So let's say your encoder value is at 10, it would reset it back to 0. And again, we are just setting it to run using encoder. Now here, this just breaks the robot. or sets all the powers to 0. So that is how you set up your motors inside of your class with all your hardware. Next, let's go over acceleration and deceleration. So first, what you want to do is you want to create a variable acceleration inside of your teleop opmode. So you want to have a public double acceleration, whatever, and you want to set this to 0.3. Or if you wanted to accelerate faster, you would set it to a higher value. Or if you wanted it to accelerate slower, you would set it to a lower value. So this is just your preference. Now you want to create 3 more variables. I know I have a 4th one right here, but this was for another motor that we had inside of our slider. So you want to have a move y-axis, move x-axis, and a pivot turn. Or you can name them X, Y, X, and turn. Whatever it is, as long as it relates to Y, X, and turn. So it's just easy to use. And you want to set the Y to gamepad1.leftStick Y. So this will be for the Y movement of the gamepad. And you want to set the X to minus gamepad1.leftStick X. So this will reverse the gamepad X. And now for the turn, you want to set it to the reverse. You want to reverse gamepad1.rightStick X. So this will be for turning. So now you want to create 4 more variables for target powers. So you want to have a target motor name power. So let's say you have a target front left power, target back left power, target front right power, and target back right power. So you want to set this to the joystick values. So for the front left power, you want to set it to the y-axis plus the x-axis plus the turn. For the back left, you want to set it to the y-axis minus the x-axis plus the turn. For the front right motor, you want to set it to the y-axis minus the x-axis minus the turn. And for the back right, you want to set it to the y-axis plus the x-axis minus the turn. Now, these were just the target powers. Now you want to create 4 more variables for the actual power. And you want to set this to acceleration times the target power minus the current power. So this would be how far you are from the target power, and it would multiply this by acceleration. And you want to add this to the current power, so plus equals right here. And you want to do this for all 4 motors. So once you've done this, you're done. Now you want to make sure that you use this whenever you call set power. So for flmotor.setPower, we have drive train speed, which is just a double variable 0.6 times FL power. So this will make it accelerate and decelerate. Okay, so here's another explanation of how acceleration and deceleration works. So let's say we're at a power of 0 and we want to accelerate to a power of 1. Well, the quickest way to do this would just be to accelerate really fast from 0 to 1. And that would seem fine. But the reason that this doesn't work is it would create a lot of momentum. Now, the reason we don't want too much momentum is because of this. Let's think in terms of distance over time. So right now, we're at a position or distance of 0. And our target distance or position is 30 centimeters right here. Now, if we accelerate very quickly from 0 to 30 centimeters, what will happen is that, yes, we will reach our target position, 30 centimeters, but we will overshoot because of this momentum. And now remember, whenever we apply power, there will always be momentum. So, once we overshoot, we'll try and fix it, but then we'll undershoot because of that momentum. Then we'll overshoot again, undershoot, and so on. And we would have many oscillations. And we don't want this as it takes longer to get to our desired position. So, one way we can fix this is instead of going directly from 0 to 1, we can start at 0 and slowly accelerate to 1 right here. And now the slope of your line, in our case it's 0.3 because this is whatever you set your acceleration variable to. We set it to 0.3, you might have set it to 0.5, and that would make your robot accelerate faster. But this would mean more oscillations. But if you set it to something as 0.1, it would get to your target power a lot slower, but this would mean a lot less oscillations. So, again, if you're at 0 and you accelerate at 0.3, then you would reach your target position and you would overshoot a lot less than if you directly accelerated from 0 to 1. So then you overshoot just a little, and then you have many less oscillations. And if you had 0.1, you would have even less oscillations to come from here, here, and so on. So I hope that helped you understand how acceleration and deceleration worked a little bit better. So now let's go over how to implement accurate movement into your robot. So to do this, you'll first need to know what encoders are. So encoders are basically a device that measures how far something has moved, and it does this by checking how many times a disc or a wheel has turned, and from that it can calculate the distance that the robot has moved based off the gear ratio, which is how many times the motor turns in comparison to how many times the wheels turn. So if you had a 1-to-1 gear ratio, 1 turn of the motor would equal 1 turn of the wheel. If you had a 2-to-1 ratio, 2 turns of the motor would equal 1 turn of the wheel, and so on. So this is one type of encoder. This is a optical encoder. So how it works is you have a disc with holes inside of it, and you have an LED light, and here you have a photosensor. So basically every time this turns, and these are like a set distance apart, every time this turns it can check, oh, it moved like, let's say, 1 centimeter, because the light would shine through the hole and be read by this photosensor. There are other types of encoders too, such as magnetic and mechanical. One more thing you should know about encoders is counts per revolution. So that's basically how many times a encoder counts let's say like a tick for 360 degrees the motor's turn. So let's say the motor starts here. If it turns 360 degrees, how many times would the light be detected? So in this case, you would count up all of these, and that would be the counts per revolution. So once you have your encoders and motors set up and configured, let's go over how you can actually read them inside of the code. So a function that you want to use to read the encoder is getCurrentPosition. So what you want to do is whatever file your motor was defined in this case it's this file called robot, and since we're coding inside of this robot class, we use this dot the motor name. So you want to do the name of the file dot motor name dot get current position, and that is how you read the current position of the encoder. Another function is set target position. So this will set a target position that you want your motor to move to using the encoder. And how you can actually run to that position or go to that position is dot set mode and then DC motor dot run mode dot run to position. We have gone over these functions before, but there is run using encoder, and then there is stop and reset encoder. Okay, so now that you know how encoders work, let's actually start implementing our accurate movement. So here I have a function called start drive to position with a parameter of speed and a parameter of distance. Now what you want to create is 4 variables. You want to create 2 target variables, a target left and a target right, and average variables, average left and average right. You want to set the average left to your front left motor dot get current position plus your back left motor dot get current position divided by 2. And same thing for the average right. Front right motor dot get current position and back right motor dot get current position divided by 2. Next, you want to set your targets to the average plus the distance times counts per centimeter. We'll go over this a bit later. Typecasted to int. So basically, what typecasting does is it converts one data type to another. So let's say you had a double or a float. It would convert that to an integer variable. So now for the counts per cm. Now, if you look up here, you can see counts per centimeter. So this is basically the counts per motor revolution, which we went over. So this is how many ticks per revolution. So basically how many times the encoder counts the light or whatever type of encoder, how many times it counts a tick per revolution, plus times drive gear reduction. So this is basically your drive gear ratio. So 1 is for 1 to 1. So again, like I explained, how many times your motor moves compared to how many times your wheels move. So for our robot, we have a 19 to 1 ratio. So the motor has to move 19 times to move the wheel 1 rotation. Then you divide that by the perimeter, which, if you learned this in math, is basically the diameter times pi, or 2 pi r, which is basically diameter times pi. After setting your target positions, you want to set the actual target position of the motor. So motor name dot set target position, and you want to set this target position to this target variable right here. So for the left motors, you want to set it to the left target, and for the right motors, you want to set it to the right target. Next, you want to set the mode of the motor to run to the position. So motor name dot set mode DC motor dot run mode dot run to position. And then you finally want to start the motion or start moving. So you want to do motor name dot set power speed, which is up here. And by the way, distance is also this variable right here. Now, one more thing. To stop all the motors, here you just set all the powers to 0 and you turn off run to position. So just set it back to run using encoder. Now, it's the same thing for strafing, except you'll have to just change the powers a little bit. Now, when you actually want to move your robot, and you want it to move accurately, and this is mainly for autonomous, but you can do this in Telia, you want to do the file name on which the function was defined, dot the name of the function, in our case, start drive to position, then the speed and the distance. So here, it just moves the robot 8 centimeters with a speed of 0.5. And again, right here, we have stop drive motors, which just sets off run to position and just sets all the powers to 0. Okay, now we will go over how to use Roadrunner for motion control and motion planning. So the first thing you want to do is to go to learnroadrunner.com. We will also provide some more links which have helpful information on how to set up Roadrunner. The first thing you want to do is to download Roadrunner. So you want to navigate to this GitHub link in the installing page, and then you want to download the zip file and extract the folder into any directory. Open up the folder in Android Studio, and then you have everything you need to get Roadrunner up and going. And so this is just using the quick start, which I recommend, and there's also installing it inside of your project. So you can read through this if you want to install it inside of your project and not start a whole new project. So next, you want to set up your Roadrunner properly. So first, you want to set up your drive constants file. Okay, so here is our drive constants file. So the first thing that you'll see in your drive constant file is the ticks per revolution. And you want to make sure this is configured to your motor. So our ticks per revolution on our motor is 538. Then you want to set your max RPM, or revolutions per minute, and ours is 312. Next, if you're using an encoder, you want to set this run using the encoder to true. Okay, so right here you have PID. You don't need to worry about this right now, but you will need to set this up eventually. So there's the page on Roadrunner, drive velocity PID. So when you're setting it up, you want to make sure if you are using encoders, you set up PID properly. And I'll provide some more links on how PID works in the description below. Next, you have your wheel radius, which is pretty self-explanatory. It's just your wheel radius in inches. Then you have your gear ratio, like we mentioned before, and this is our 19 to 1 gear ratio. And then you have your track width, which is basically the distance between both wheels. So if you have your back right and your back left, you would just want to measure the distance between those in inches. So ours is 10.5. So this right here is feed forward. It is used if you're not using encoders or if you're using dead wheels. So dead wheels are basically a non-powered wheel, which is usually an omni wheel, and it's used just like an encoder to measure where you are in the field and how much you have traveled. So I'll give some links in the description of how omni wheels work, and some helpful links that you can use to learn about omni wheels. Next, right here, you have max velocity, max acceleration, max angular velocity, and max angular acceleration. So this is pretty much self-explanatory. Your max velocity, your robot can move at. The max acceleration, your robot can go at. And the max angular velocity, so just how fast it can go. So here you have 4 variables, just your max velocity and max XL, and the same thing for the angular. So it's just what's the highest velocity, linear and angular, and the highest acceleration, linear and angular. Here are just some functions that are used in other files, so you won't really be needing these that much, but it is used in other files inside the Roadrunner library. So that was a brief explanation of the drive constants file. But a quicker way to set up your drive constants file is, instead of going through the code one by one filling in the variables, if you go to the drive constants page on learnroadrunner.com and you click this button right here, Configure Me, you can now set up your drive constants file much easier. So here, if you're using these two chassis, go build a straight for chassis version 1 or version 3, you just click this, next, and it sets up your file. You can download it and extract it in Android Studio. Or you can set it up where you're using your own. So you first want to choose what type of motor you're using. So we use the 5203 series, and its max RPM is 312. Ticks per revolution I am unsure of, but I think it was 528, which was in the code. 538. And so this, you want to look at your motor specs, which you can find on your provider of your motor. Like if it's Rev, you can check the Rev website, or Go Build a website if you're using a Go Build a motor. Next, you want to have your gear ratio. So ours was 19 to 1. So if 19 turns of the motor is 1 turn of the wheel. Now we are using these wheels right here, so just the wheel radius, ours is 9.6 millimeters. Then your track width, ours was 10.5. So that's just the distance between the two wheels. And if you're using encoders or not, so we are. And now you can download your file and copy paste the code into Android Studio. Next, once you have your drive constants file set up, you will need to set up the rest of Roadrunner. So if you go to high level overview, it has a nice graphic of how you're going to set it up. So you set up your drive constants, then you do your localization test, and if you're using encoders, you set up PID. If you're not, you set up feed forward, and then you do your straight test, track with tuner, turn test, localization test 2, and your follower PID, and then spline test, and then you're done. So you can read through this. This is a basic explanation, and if you want more in depth on each section, you can click on it, the link that is at the bottom of each section right here. So if you click drive velocity PID, it'll take you to drive velocity PID right here, or you can just scroll through this sidebar right here. So once you have everything set up for Roadrunner, trajectories should be working properly. So there are vectors and poses. These are the main things that are used to write a trajectory. So a vector 2D is a 2D vector, and it has an x and y coordinate. So you just do vector 2D, my vector equals new, vector 2D, and then x and y. And you have a pose 2D, which will have an x and y and the heading. So here you have a pose 2D, my pose equals new pose 2D, 10, minus 5, and then a direction, so math.to radians, which will just convert degrees to radians, and then 90. Now, here's an example of a trajectory. You have the op mode, then you have once the op mode is run, you initialize your hardware map, you create a trajectory, so you first strafe right 10, and then you go forward 5, and then you build. So this build just basically builds the trajectory so you can run it. And so how you create a trajectory is trajectory, my trajectory equals drive.trajectory builder, and then you have your pose 2 right here. So you wait for start, and then if stop is requested, you return, so you exit, and then you drive.follow trajectory, my trajectory. So you would think this would work, right? So it won't work because of something called discontinuities. So if you've taken pre-calculus or algebra 2, you know this, but basically, because of momentum, a robot physically can't go straight from strafing right to forward, because there's always going to be some slight momentum which will cause the robot to go in an arc before it can go directly from strafing and then moving forward. So one way to fix this, an easy way to fix this, is to split your first trajectory into 2 different trajectories. So you first strafe right, and then you go forward. So this will stop and then go on to the next one, and then you just call this follow trajectory twice. Or you can use splines. So splines are a bit more complex, and I won't go over them in this video, but you can read over them on the trajectories overview page. So if you have a custom start position, then you will need to set a pose estimate. But by default, your localizer position is set to 0. So here you have a start position of 10, -8, and then heading 90 degrees. So what you need to do is you need to call drive.setPositionEstimate or setPoseEstimate start pose. And you need to call that before your first trajectory, and you only need to do that once. Now, trajectories versus turn. So basically, if you want to turn, all you have to do is call drive.turn, math to radians, and then however many degrees you want to turn. So going backwards. So basically, all you have to do to go backwards is add a true right here inside of this line of code. Your drive.trajectory builder. So here is another example from the Roadrunner library. So basically, it just moves your robot backwards and forwards. So you initialize your hardware map here. You have 2 trajectories to move forward and backward. And then you wait for start. And once the op mode runs, you call the trajectory. So you follow the trajectory, trajectory forward, and then you follow trajectory, trajectory back. And this just keeps looping between the 2, so it'll move forward and backwards. That was it for this tutorial. Thank you so much for watching. If you have any questions, feel free to ask them in the comment section below. Any topics that were mentioned in this video, you can find links to learn more about them in the description below. I really hope that this helped you and that you learned something new. See you next time. Bye!